Hello, I'm Channa Bankapur. I'm going to discuss my solution to the LeetCode problem, maximum difference between node and ancestor. It's today's daily challenge in LeetCode. The problem definition is we need to find the maximum possible difference between two nodes where one of them is an ancestor of the other, right? So among all pairs of ancestors, among all pairs of nodes where one of them is an ancestor of the other, we need to find the one that has maximum difference, right? So let's go with this example, and there are obviously various pairs of node and an ancestor. If you take few of them, suppose the difference between 8 and 3 is 5. The difference between 8 and this one is 7, and say 10 and 13 is 3. 8 and 13 is actually 5, and 8 and 4 is actually 4 here. So if you figure out all the uh, uh, you know all the pair of nodes where one of them is an ancestor of the other, the difference we can keep finding it, and the maximum among them is 7 in this example, right? We can try it as an, I haven't tried every pair here, but yeah, 7 is the answer for this example. So how do we find something like that? So I'm going to use a simple recursive idea where I'm going to assume that I already know the min and max of a subtree or a whole tree, and I can use them. I can use the min and max of the subtrees so that I can find the difference also, right? Because when you have a node and all the nodes in a subtree are all successors, that means for all those nodes, the current root is an ancestor, right? So that's what we need to do. And if it's a leaf, obviously the min and max is itself, and there is nothing called maximum difference for this because there is only one node, right? That's why we need at least two nodes in the tree to have a meaningful difference, right? So what we can do is I'm going to just write min and max of each of these subtrees. So min and max of this the subtree starting at 4, starting at 6 is going to be max is going to be 7, and min is going to be 4, right? So this is that pair. And for subtree starting at 3, the max is 7, but min is 1 now, right? Because there is a 1 down here on the left side. So for this, the max is 14 and min is 13, and max is 14, min is 10. And in this case, max is 14 and min is 1. Now, knowing the min and max of a subtree, at a given node, we can actually find the maximum difference involving the current node with the follower there, right? But it's not for the whole tree. That means we are not considering every pair. We are considering a pair where one of the nodes is the current root itself. So to get the answer for any pair, what if we solve this subproblem here first and the subproblem here, which is left and right subtrees, and we have an answer for that, right? Whatever the max diff. So the max diff of these two and the max diff that can be obtained by taking the difference of the current node with min and max of left subtree and min and max of right subtree. So among these 6 possible answers, I'm going to find the one, right? What are those 6 possible answers? So if I'm processing at root, imagine root is not null because we're not going to allow that. So if root is not null and there is some left subtree and right subtree, and we already know their answers, right? Their max diffs. So those are the two values. So it's going to be max diff of left, right? And max diff of right. So these are the two answers we get from the subproblems, like recursively solving them. Along with these two, there are 6 other contenders. One is the current root minus the min of left, right? So the absolute difference, obviously. And similarly, the current root minus, as in the value of the current root minus max of the left. Similarly, the difference with the min of right subtree and max of right subtree, right? So these are the 6 different values. We need to take max of all of them, right? It is going to be the maximum of all of these things. So if we do that, we are going to get it. But yeah, so can we do it in linear time? Yes, we can. It's not like we need to find the min and max of every node separately and then use it. While returning this, whatever the answer, the max diff, we can also return min and max. That's how my return value is gonna have a is going to have three values. I'm going to use a vector to return all the three values. And that's how, and finally, I'm going to use only the first one, which is going to be max diff, right? So, but the other two values, like, max value, or sorry, the max node and min node of the left and right subtrees are actually the current tree now, are going to be useless at the top, but for the subtrees, except for the original root, these are all useful because the parent is going to make use of them, right? So these are the three return values at every node, right? So let's look at the code. I hope the idea is clear and it should work in linear time, linear to the number of nodes. So here is my code. So the original function, whatever is max ancestor diff, because that needs to different return only one value, but I'm returning three values. So I'm having an helper function called f, so which is going to take the root at the moment, and it's going to return three different values. So among the three, the first one is the one we are interested in. That's why you look at this, I'm returning the first of those three values. The second and third are essentially max node and min node of the whole tree, right? So that's the recursive function I'm going to have. So look at this. I prepare the return value, which is the max diff and the min max node and min node. For the max node and min node, I'll start with the current root node itself. But for the max diff, because we want to maximize that value, I'll start with the like int min, which is essentially like minus infinity. See, there are 6 values we need to compare and take the max. I told you, right? So we're going to do that. So if there is no left, I'm not even going to call. That's why I ensure that this function call f will never have root being null. That's why I don't even have to worry about root being null here, right? So we know that this root is not null in the beginning, and we'll never call this function f recursively if that root is null. So that's why if it is null, I'm not even going to call. So if it is not null, then only I call recursively here on f of root of left. So I get a vector v. So as I told you, the first value, the v of 0 is going to be the max diff of the left subtree, right? So that I'm considering here. So this is the first one, and the difference with the root value and the max of the max node of the left subtree, and then again I'm going to comparing that with the min node of the left subtree. So these are the three things with respect to the left subtree, and there are corresponding three other values we need to compare on the right subtree if at all it exists. And the max of all of these 6 values is what is interesting to us. That will be stored in result of 0, right? Because when I'm returning the first of the three, the first value of the three values in the vector is going to be the max diff. Second is max node and third is min node. So that's why I'm keeping track of max node, min node also. So result of one is going to be the max of because for max node and min node there are three contenders. One is the current node itself and the result of the left subtree and result of the right subtree. So for the max node, the to start with, it is the root itself, and then I'll compare that with that of the max of the left subtree and here max of the right subtree, right? The similar way we are going to do it for min node also, right? So that's how I'm going to return a result which is going to have all the three values, right? So the code is little longer here, but if you see it works efficiently with linear time because I'm calling this function for every node exactly once. And this whole part, the non-recursive part of this whole function is actually big O one time, right? So that's why this should work in linear time. So overall function should work in linear time. And the space complexity, we don't take anything other than the stack. So the stack space is going to be obviously whatever the depth of the tree. So or what we say height of the tree. So big O of height of the tree is going to be the extra space. The extra space is only for recursion, right? So otherwise the idea is much clearer. So recursion is the way to go. All right. Let me submit and show you that it accepts. It accepts and it works pretty fast. I have seen this. All right. So yeah, if you have any comments on this, please let me know. Otherwise, please like the video and subscribe to the channel. Keep coding every day, and thanks for watching.